pleasure to welcome you all back after a weekend. I hope you had a good break. The first set of course is done. Are you ready for the next group? Right. So it's a great pleasure to welcome Professor David Spiegelhalter from Cambridge. He is the Winston Professor for Public Understanding of Risk in Cambridge. And this is his second visit to Ames. So 3 years ago, that's 2.5, we organized a very interesting meeting called Diversity in Mathematics. And we wanted to cover many fields, and David was generous enough to come and lead that part for statistics. So this time he'll be telling us about probability and statistics, and I see there are some experiments that we've got really to start with. So David, we'd like to welcome you back, and glad that you've come. Thank you. Look forward to your course.
All right, thank you very much. Oh, right, great. Okay, it's a great pleasure to be back here. Slightly nerve-wracking. I think I'd expected a slightly smaller group, and so a lot of people here. Yeah, please. So first of all, please say if I'm not clear what I know. English isn't the first language of everyone here, and so please say if I'm not speaking clearly, or if I'm just speaking so slowly that it's getting too boring. So I'm going to be doing this course on probability and statistics. It's going to be a mix of sort of theory and practical questions in the computer lab. So that, for example, today I think we'll probably run about an hour and a bit here, and then all move upstairs. And that's probably how it'll go. But of course, I'm not quite sure how it's going to go. This will depend on you, I think. So, okay, this is what we're going to try to cover over these 3 weeks. And again, I put possibly. The first week really is probability. And that covers basic laws, random variables, discrete and continuous, moments, expectation of variance, change of variable, Bayes theorem, and in particular distributions. Normal, binomial, geometric, etc., etc. Lots of distributions that we're going to use for statistics. So really, I'm doing probability for statistics. Now, actually, I'll come to that in a minute. I'll try to find out a bit about your background in a moment. Then the idea is, so the second week, we can use that probability to talk about what one might call rather traditional statistics, estimation, sampling theory, maximum likelihood estimation, hypothesis testing, Neyman Pearson, etc. All of this hopefully illustrated with practical problems, real-world problems as much as possible. Because what we're building up to is something in the third week, which is statistical modeling. And this is where I think it starts getting really cool, because we're going to be dealing with real data, complex data, and the idea of relating these so that we're generally trying to relate a response, for example, mortality rates or occurrences of disease, with possible factors, such as geography, etc., etc. And that involves regression modeling, in particular generalized linear models and some Bayesian analysis. And then, I mean, who knows what we'll get to at that stage. I hope some realistic, practical, difficult problems. That will, not necessarily, they'll involve some mathematical thinking, but also involve some perhaps background understanding of the world. So how I'm going to do this is to do lectures, but also practicals using SciPy. I use R myself at home on the whole, and I think you're going to be, if you haven't done R, you'll be doing it later. But actually, in order to fit in what you've already done on Python, we're going to be using SciPy, and SciPy.stats contains a lot of routines for doing some of these things. And there will be also, more theoretical questions and open questions of different difficulty. And please help each other. And please, I hope also we're going to be dealing with, although it's quite a big group, some interaction in the class, but I'm also hoping that you will be helping each other in your work. Okay, so probability. This week, we've got 5 essential sessions, and I'm going to start today on what you call intuitive probability. And this is, before we start getting more mathematical, more formal, the idea of just this intuitive idea of how probability works in the real world, using the sort of stuff that, the sort of dice and, all this kind of thing that are used to teach these things. Tomorrow we'll be talking about, it's still restricted to these rather simple problems of equally likely events, or sort of counting how many possibilities there are in the world. And then in the third lecture, I think we get on to something a bit more formal, because I think we do have to study the more formal theory of probability theory about random variables, discrete distributions, but then we get on to expectations and variances, various difficult problems. And then we'll start introducing some of these important distributions, binomial, geometric, etc., etc. Continuous random variables, then we start getting a bit heavier. We start looking at change of variables, etc. And finish off with Bayes' theorem, the start of Bayesian analysis. Now, I'm definitely focusing on the skills necessary for statistics. There's all sorts of stuff in probability that I'm not going to do. I'm not going to do random walks, branching processes, Markov chains. All this is very nice, but we're not going to do it, I'm afraid. So I'm really sorry if that's what you wanted to do. Now, can I I'm not quite sure of the best way to do this. I'd really like to know for how many people this is all going to be complete revision and how many people this is going to be fairly new. So let me, what's the best way? If you put your hand up, I won't test you. So if I say a topic and you put your hand up to say you've done it, I'm not going to start testing you. It's all right. So don't be worried. Tell me the Kolmogorov axioms. Come on. No, I'm not going to do that. So have people done, who would have done a fairly mathematical course on probability that would involve axioms of probability, like Kolmogorov axioms or something like that? So right, okay. So some pure mathematical people have done that. Well, this will seem, probably rather non-mathematical compared with that. Okay, who have done things like just, basic things like distribution, binomial distributions. So if I said binomial distribution, who would say, yeah, I've done that? Yes, only about half of that thing. And would that tend to be in applied areas of engineering type of applications or more theoretical? Is that too difficult to say? Somebody say something. Where have you met the binomial distribution? Sorry, where?
Just the theory. Just the theory.
In just the theory of it, yeah, okay, fine. All right, so it looks like, while some people will have had some mathematical stuff, I think I'm okay in starting from this material and going over it. Okay, great. There's some books. I looked through the library yesterday. And just in order of basicness, for people who haven't done too much, certainly, this is an A-level book, but it's got a very nice section on probability. There's only one copy of that. There's lots of copies of these, about 8 copies of these. I like this. It uses probability trees, which I'm going to be using a lot of. And then we get into probability books. This Grimmett book, Grimmett and Welsh, is a very big selling book, and it's rather good. It's quite short. Quite terse. This is the absolute classical book, advanced, but quite readable, really. It's remarkably readable. This is a bizarre book, very eccentric, very strange book. I love it. But it's got a mixture between almost a conversation. He writes it all, I think this, I do this, and some quite mathematical depth. So the pure mathematicians might quite like this, which goes into basic topics in more depth. So these are all there. Okay, and also these are all on the website. For the course website has already got these lectures, these notes are all up there, and the exercise class. So everything will be up on the website. It's there already. Okay, first lecture, intuitive probability. And I love history. I'm going to do a little bit of history just because the historical problems, things people started with 500 years ago, are actually, or 400 or 500 years ago, are actually still, they're good examples. They're quite challenging. So I'm going to get you to solve a problem from the 1650s in this one. So I'm going to talk about early ideas. Whoops, what have I done?
Log out.
How did I log out? Help! Help! No, I go all to pieces with this sort of stuff. Okay, I logged out. Anyway, I'll be doing some intuitive work, historical things and from there I'll get into more. I've forgotten what I am doing now. Until I've got some prompts. No, did it not like that?
No, I'm not sure what happened.
Yeah, okay. I must have kicked something. Fermat's last. Well, we're doing Fermat. Why I've got Fermat in there is that probability started from gambling. And gambling 400 years ago, the gamblers really wanted to know the solution to their gambling games they were playing. And so they consulted Fermat and Pascal in 1650s or so, and they essentially invented probability. The idea of probability and how to manipulate it was invented 1650, so that's, it's not even 350 years ago it started. And amazingly, probability was so late. People used to play games all the time, throwing things. I mean, the Egyptians were throwing dice or objects to play games thousands and thousands of years ago. Everyone's thrown it. Actually, I'll start off now. Can I pass these around? What the people used to do before they had dice, nice even dice, although the Egyptians had dice, I think 3,000 years ago, they'd already be able to make really nicely balanced dice. Apparently the dice in the Cairo Museum are fantastically balanced. They're beautifully balanced. But before that, and simultaneously with dice, people had these, which are knuckle bones, astragali. Has anyone ever played with these? These bones? They're from the heel of a sheep or a goat. So it's the bone just there. I did these myself. I bought a leg of lamb from the butcher and cut the end off and boiled them up and then got it. It's really disgusting. You're getting in there. And in the middle of the heel, you find these beautiful bones. And this is what everyone used to throw. And there's only 4 possible ways they can land, unlike a dice. And it's not symmetric. So they're not equal. And the Venus throw was a particular throw where you threw 4 of them and they all came up on different sides. That was particularly auspicious. But nobody actually ever counted how often they came up. So they used to gamble with these and yet never did any maths on them. Can I pass these around? Just pass them around. Just have a little play and have a go at throwing them. They're quite nice. I've only got a couple. But I don't know do we ever get lamb in the kitchens? If they ever get legs of lamb, can they keep the bottom bit? And we could all get them to boil them up, or we could all hack them apart, because they're beautiful things. So it's amazing that for centuries people gambled and played games and never did the maths until 300 years ago. I'm sure when you were growing up you played games. Did everyone play games where you threw things, some random stuff like dice or coins or other things where you didn't know what was going to happen? I'd love to, I won't stop it now, but I'd love to hear about any games that you used to play, because I'm really fascinated by, board games, you throw things, you move along, and not games of pure skill, but where pure chance comes into it. But actually it wasn't the, I know, well, pause, and pass these around. I haven't got enough for everybody. There's just one between 2. Can I just give you all one between 2 dice, just so we can do, let me track out some dice. Actually, I don't think I've got enough of that, have I? Let me keep going. Not everyone can have them. So this is what people were throwing. Dice, yeah, here we go. A couple there. Well, I think I'm going to run out. Oh, well, let's see what I can get on. Oh, no, there's 2 there. I think you can only have one. One. Sorry about that. Okay. Okay. So the dice is really important. Technically, it's a randomizing device. One of the things I'm going to get you to do afterwards is to write a computer program to simulate a dice, because we can't keep on throwing it thousands of times. It will get too boring. Okay? Stop throwing. You can throw in a moment. So that's what they used to throw. So that's what I said. Nobody did the maths. Knuckle bones, they're known as. And nobody did the maths. Extraordinary. Until this guy, who was an Italian doctor, an obsessive gambler. All he did was gamble all his life. He's lost all his money, everything. He was always in debt because he just gambled. But he wrote the first ever book on gambling. And all he was concerned, and basically it was a very simple thing, because before him, people hadn't realized that when you threw 2 dice and added up the total, that you were more likely to get 7 than you were to get 2. And you think, actually, that's pretty obvious, isn't it? If you throw 2 dice, add them up, you're more likely to get 7 than 2. And nobody had worked that out. And he's the first one who actually went ahead and listed the possibilities of what you could get when you threw 2 dice and invented, although he didn't use these words, a sample space of equally likely events. So we're going to I can start drawing this out, I'll do it on here, of another thing he didn't do, but I'm going to do, use this idea of a probability tree, which represents a tree of things that can happen, and there's going to grow out like this. So this is, throwing the first dice. Now, if I was going to be correct English, I'd say die, single die, dice. I'm not going to be correct English. I'm English, I'm allowed to use bad English. So I'm going to say dice. And so what it does is represent a tree that this one could come out here and be a 6, be a 1, or a 2, or a 3, or a 4, or a 5, or a 6. And then the second one, let's say the first one was a 3, could come out and be a 1, 2, 3, 4, 5, 6, producing a joint outcome of 3, 1 down to 3, 6, an ordered pair of numbers, and you can add these up, and there's a total of 36 possible outcomes. And he's the first one who realized there were 36. And if you add up the sum of these, so that would make 4, that would make 9. If you get a 1, 1, that will make 1, 1, that will make 2. What he did was work out that when you looked at the number that made 7, you had a lot more. You had 6 possibilities of making 7, whereas only 1 possibility of making 2. So it's completely intuitive. Without any real maths, he did that. Worked out that getting a 7 was much more likely than getting a 2 because there's more possibilities. Okay. We can think of what he did. The best way to think of what he did is to draw actually what I've drawn there, but think of it as a frequency tree. Think of what would happen in 36 throws. So if you did 36 throws of 2 dice together, you'd get 6 going, you would expect, by some assumption of symmetry, whatever, 6 to go up here, 6 there, 6 there, 6 there, 6 there. And then out of these 6, you'd expect 1 there, 1 there, 1 there, 1 there, 1 there, 1 there. And so you'd end up with a total here. This is the outcome. Oh, I haven't written this my board work is terrible. You'll have to get used to that. That's the outcome there. And I'll get rid of the sum there. We'll just say here, the total number of events, well, there's 1 there, 1 there, 1 there, 1 there, 1 there, and there's 36 altogether. So we've drawn a frequency tree showing how often these events occur. And then we realize we can do things like just add up the number that come to 2 has a total of 2. There's just one of those. But if we add up the ones that come to 7, there's, if we look at these, there's, if we look at here, the sum for 7, we find it's true for 1, 6, and 2, 4, etc., down to 6, 1. So there's 1 for each of those, and we add them up, and we see there's 6 of those, as opposed to only 1 of those. And you think, well, that's so obvious, that's so obvious. Nobody thought of that before 1570 or something like that. So we can think of these, we can add up these totals, and then think of how often these occur as a fraction of the total number of events. So if I draw this as 1 now, we see there's a 1 over 36 chance of that, 1 over 36, 1 over 36. So we've actually derived pretty well the whole of probability theory from that reasoning. These are the basic rules for manipulating probabilities in these ways, which we will, by lecture 3, we'll see how these actually can be derived from an axiomatic theory. But these are the sort of intuitive rules that arise just by thinking of the frequency with which events happen. Okay, so the rules we're going to use a lot over the first couple of days in our games and things. First of all is the complement rule. The probability of something happening is 1 minus the probability of it not happening. So the probability of a 6-6, let's do a 6-6, a double 6 is 1 over 36. And so the probability of getting anything else is 35 over 36. So that means, so the probability, I'll write this up on here, a lot of running around here. So we can say that the probability of a double 6 is 1 minus the probability of not a double 6, which is 35 over 36, which is 1 minus 35 over 36. Okay, complement rule. The addition rule says that for the probability for a set of outcomes, you add up the probabilities over the ends of the relevant branches. I should have said they're disjoint outcomes, meaning these are outcomes that can't both happen. So if I want the probability of a 7, I add up over the probabilities for the ones that add up to 7, and I get 6 over 36, so 1/6 chance of getting 7. Okay, that's the addition rule. So you add up over branches. And multiplication, if I want the joint probabilities, what is this 1 over 36? I multiply down the branches for how to get there. So I would do, what I'm going to convert this to is, this is a frequency tree at the moment, showing how often these things happen. I can turn it into a probability tree, by normalizing it, so that becomes a 6, that becomes a 6, 1, 6, 1, 6, 1, 6 down there, and then I get a 6 chance of going down there, 6 chance of going down there, and this is the normal way people would draw a probability tree. So you put a probability on each branch, and then the probability of getting to the outcome, you just multiply down the tree. And that is essentially the rule of conditional probability. Now, in these situations, these dice throws are what we say they're independent. The second dice throw isn't influenced by the first dice throw. So the probabilities are the same on the branches. But it's not always like that. They're not always independent. So here is an example. And you're going to be doing some of these in theory as well. Jelly beans. Jelly beans? Who likes jelly beans? I'm going to put a certain number of jelly beans in here. You may not want to eat them due to my chalky fingers. I think you mustn't look. Okay, so if I put, in here there are 3 blue jelly beans and 2 yellow jelly beans. Okay, so let's do that up here. Okay, so there's 3 blue and 2 yellow. So what's the chance of picking 2 blue? Did they fall out? Oh, that's not very good. There's no probability, yeah. 3 blue and 2 yellow, let's write that down. Yeah, that would ruin it completely, wouldn't it? It's got 3 blue and 2 yellow. And what I want to know is the chance of 2 blue, picking a pair of blue ones. Okay, so what we do for that, if we're thinking of a problem like this, and you're going to get some of the exercises like this, is we think of the first one. So that could be a blue, or it could be a yellow. So what's the chance that the first one is a blue? So what is it? 3 over 5, yeah. Pick one. Oh no, you can't look. Pick one. And it is a yellow. So there. So, okay, you're right. So it's 3/5 of going down there and 2/5 of going down there. Okay, well, now we're a bit messed up. We've gone down here. What's the chance now of picking another yellow? What is it? 1 over 4. Yeah, 1 over 4. 1 over 4. That's right. And it's a blue, it's a blue, it's a blue. So it is a yellow. If we want to know the chance of a blue, yellow, and that's now 1 over 4, and that was, what, 3 over 4, and we chose a blue. So we went down this path. So what was the probability of what we actually observed? We went down here, and then up there. What was the probability then of what happened? Yeah, 6 over, what is it? We multiply down the tree. Yeah, 6 over 20, so what's that? 3 over 310. So it's 0.3. So 0.3 chance, so not a very surprising event really. So you see, but in this situation, these probabilities had changed. They were not independent anymore. These were dependent events. Essentially what we say is, and we'll come on to this tomorrow, this was sampling without replacement. We didn't put, we didn't put the jelly bean back. If we'd put the jelly bean back, the probabilities would have stayed the same, sampling without replacement. As it is, they changed. Okay, so we'll get you to do some of those simple things, but the basic idea here is that you multiply down the tree, add up across the tree. And that's what they did a few hundred years ago. They didn't use trees then, unfortunately, but that's what they did. Okay, let's take, we can express that a bit more mathematically. It's slightly more familiar to people. A little bit more mathematically, we're going to introduce the notation of an experiment. And this is like, throwing a dice or picking something out. We've got an experiment. We've got a set of possible outcomes omega, which is the list of things that can happen, the sample space, omega. And the impossible event, 0. Nothing happens. So that's the empty set, nothing happens. So intuitively, we'll do this more formally later, but intuitively, we say the probability of something happening is 1, the probability of nothing happening is 0. So we say something's bound to happen. I am going to throw the dice, something's going to happen. The dice isn't going to disappear or of course, land on its edge or something, or we might lose it, of course. So this actually is a big assumption. We'll come to that a bit later, maybe. It's a big assumption because it's assuming you've thought of everything that might happen. It means you're not ready for surprises. So this basic mathematical assumption is something that's been subject to a lot of criticism recently. Before the financial crash, people hadn't put a probability on these terrible things, and not everybody put a probability on these terrible things happening. Nobody had thought of it happening. So from a practical point of view, this could be one of the most important, it's trivial mathematically. From a practical point of view, it could be one of the most important things. Okay, so the complement rule says that probability of event A is 1 minus the probability of the complement of the A. The addition rule says that if A and B are disjoint, at the ends of branches, we can just add the probabilities. The multiplication rule, and you're introducing this notation, which we're going to use a lot, conditional probability. And actually, the whole course is really on conditional probability. Probability of B given A is the probability of B given A has occurred. In other words, this probability, given you've already drawn a yellow jelly bean, we just multiply down down the branch to get the joint probability of both things happening is the probability of the first thing happening times the probability of the second, given the first has already happened. So this basic multiplication law for non-independent events is absolutely fundamental. But if they're independent, in other words, if the probability of the second one happening doesn't depend on the first, like dice and coins, then we can just multiply up the probabilities to get the joint probability. We can also rearrange this to give a definition of conditional probability, which is the probability of B given A is the probability of A and B divided by the probability of A occurring, which is just that rearranged. So we'll come on to that again a bit more formally, but the idea is that we've derived all these rules that we're going to build everything on from a real intuition about frequencies, about how often things happen, just by counting events. Okay, now, the other intuition is used a lot in probability, is that if we keep on doing things, things will settle down to the probabilities. So that although this actually happened, if we repeated this experiment with the jelly beans again and again and again and again and again, with this particular event, the yellow and then the blue, we'd expect to occur in 3 out of 10, in about 30% of times. And that 30%, it happened this time, and then it might not happen again, and then it'll happen. But, if we keep on and on and on and on and on, our intuition is that in the end, it'll settle down to that. Now, of course, that only holds in situations where you can repeat things. You can't always, it's always odd when you have, we're going to talk about the probability of how long you're going to live. Well, what does that mean? Because, I'm only going to have one life. It's not that it's going to be, not like throwing a dice. I can't repeat it many, many times. So only this is used as a motivation. It's not really used as the meaning of probability. It's not what probability means. It's just a motivation. Okay, and a bit of formality on this. If you do an experiment with a particular event, if you think of doing the experiment an infinite number of times, throwing the dice again and again and again, the jelly beans coming out again and again, for hours and hours, then the number of occasions that they occur in the first n replicates, if we write it like that, divided by the number of replicates, it should converge to the probability. It should, and this is, again, informal. We'll do it a little bit more rigorous as laws of large numbers later, but essentially a proportion tends to a probability in these repeatable situations. And so what I'm going to get you to do is, one of the exercises then is to write a program and run it a zillion times or whatever, and however many you want. And you should end up with a number close to the one you can actually calculate mathematically. This is only available in these nice situations though. Again, this is how we all learn probability, with dice and cards and jelly beans. But real life isn't like that. We're going to get into real life stuff where we don't know what the probabilities are. We don't know what the distribution is. We have to make a lot of assumptions, a lot of judgments. The only judgment being made now is that I haven't fiddled it. Because I could have put a couple of black ones in there, which would have messed it up. Or just lied to you. Which is, we have to assume that's not going on. Okay, this is what we're building up to. We're building up to this great gambler, the great gambler. So on this way I want you to use your die. Have a go with a dice moment, if you've got dice. So this was a gambler, and he asked Pascal to help him with a problem. They played betting games where it was sort of even. They both put the same amount of money in, and the person who won took all the money. So they might both put, so many rand in, so many, I don't know what they were, livres or something like that in those days. They put a pile of money in, and whoever won the bet took it all. But they put the same amount in. And he used to bet people that he could throw a dice 4 times and get a 6 at some point during the 4. So, at least 1 6 in 4 throws. And he used to think he could do that. And he also used to play another game where he used to throw 2 dice 24 times and bet that he could get a double 6 in that time. Now, let's see your intuition. And I've forgotten the answer. Which one, do you think, that first one, do you think the odds were in his favor? In other words, do you think it's more likely than not, a more than 50% chance, that if you throw a dice 4 times, you'll get 1 6? Now, don't do the calculations in your head. I bet you're all trying to do the sums in your head. Okay, who thinks it's more likely than not? That sounds, that's a good bet. It's more likely than above 50% chance. Who thinks that? Yeah? Who thinks it's less than 50-50? Anyone got an opinion? Okay, let's do a little test. If you've got a dice, and as you do it once and then pass it on, just throw it 4 times. So everyone do it once. Throw it 4 times and see if you get a 6. Okay, just do it once, and then remember and after you've done it, pass the dice on. Just remember whether you got a 6 4 times. If you get it the second time, you can stop. If you've got some time, you do the sums in your head. Nah. Nope. Nope. Okay. Have you all had a go? You all had a go? All right then. Who, when they threw it 4 times, who got a 6 during that 4 times? Okay. Now we should hands up high. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. None of you got 6 this time. Okay, who didn't get a 6 this time? Right, it should be all the rest of you. But if people who didn't, I'll just count. Hands right up. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And that's not a bad result, because it's very close. Okay, here's the maths. Actually, no, I won't do the maths there. I'll do the maths on here. Okay, the maths, there's a couple of tricks in doing the maths of this. It's really good to learn. The first one is when we're drawing the tree, we don't have to do 1, 2, 3, 4, 5, 6. We could just do 2 branches, because we're only interested in 6 or not. We could do 6 or not 6. I'll do 6 complement, which means 1 to 5. Now that's the first dice, so we might throw it the first time. If we get a 6, we can stop. If we don't, we can go there. We not get a 6, we get a 6, we stop. If we go there, with the first, we might stop. And if we do that, and 6, we can stop. So that's the 4th time. So the event we're interested in is whether we get a 6 either in the 1st, 2nd, 3rd, or 4th. That is actually a very complicated event when you think about it. That's actually quite a complicated thing, because to work out the probability of that is kind of complicated. It turns out, you can see this, it's much easier to work out the probability of this, which is not getting a 6, and then do it by subtraction. So you use the complement rule. And we find that for a lot of these tricks, if you ever see a problem that says the probability of at least something, which is a very complex compound event, look at the complement, which is obviously a very much simpler event, probably not getting it. Okay, so actually what we want is 1 minus the probability of this. But these are independent events. The probability of the first one is 5, 6, 5, 6, 5, 6, 5, 6. So to work out the probability of not getting a 6, whoops, what do? Multiply down there. And then we get an answer which is 5 to the 4th over 6 to the 4th, which is something or other. Go on. All right, something. Hang on, I've done it. Okay, here we are. Here's the rule. The probability of not getting a 6 on the 1st, and not on the 2nd, and not on the 3rd, which is 1 minus 5, 6 times 5, 5, 7, 5, 6, which is, I'm sure some of you were doing this in your head already or on a piece of paper, 625 over 1296, which is the 1 minus it is very close to a half. It's 52%. So there's no wonder, actually to get exactly 2020 was kind of unlikely. Actually, we'll do that. We'll work that out later. What was the probability of getting exactly 20? We'll do that in the 3rd lecture. So there was probably getting exactly 2020, but it was very close. So it was slightly in his favour. So he used to win slightly more than often. But then they did this other thing, which is throwing the 2 dice 24 times and wanting a double 6. So that's one of your exercises, both to do it in mathematically, and then to write a program to do it. The point is that with these simple things, we can do them mathematically. But we're very quickly going to get to situations where we can't do the maths, and we have to use the simulation method to evaluate these probabilities. Okay, so does that look okay? So it's rather informal so far. Intuition, multiply down the tree. Okay, let's get on to another thing, which is conditional probability. Conditional probability this is rather important. This is the start of what we call Bayesian reasoning, which we're going to do quite a lot of Okay, here's some data I've made up, because it might not be, I don't know how plausible it is. This is to do with gender and preference for football or soccer, whatever you want to call it. So what I've done is produce, let's pretend I've done a sample of 100 people. And I've got female, A, and a complement. A is being female, and B is A, complement's being male. And I asked 50 women, and I did a sample of 100 and found 50 women and 50 men. And then I asked them whether they liked football or not, or soccer, whatever you want to call it, and not like. And I found 40, as I said, I made this up. 40, 30, 20, 30, and so that makes 40, and so 60. So now, is that plausible? No, okay. Let's do a little experiment. Okay, so that says that, you see, what we can do now is to construct a probability tree. We've got an overall probability. We can divide by 100. You see, there's no, what am I doing? There's not enough board rubbers here. Hop, 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 hop. I need more board rubbers. Hop, 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 hop. Back we go. Actually, no, I don't want to be here either, so I want to be over here. We could, first of all, produce a probability, turn these into probabilities by dividing them all by 100. And we find 0.10, 0.40, 0.40, and 0.20. So that says that out of my 40% of my sample, 30, oh, sorry, thank you. 30% of my sample were men who didn't like football, and 40% of my sample were women who liked football, etc. So that's looking at the joint outcomes. It's actually a joint probability, turning from a frequency table to a joint probability distribution. A big assumption there about is that reasonable probabilities? You know, do you think, yeah, they don't look very reasonable to me. Let's check them. So the other way to view it, and I'll come on to this one, is we can draw it up as a sequence of conditional probabilities. We can say, well, first of all, we sampled 50 men. We picked 100 people, and 50 were men and female, and 50 were male. A, female. And then, of those 50, another way that we had, what did we have? Out of the females, we had 40 liking football, and 10 not. And then we had, what's the number? Sorry, what's that? 20 and 30. Yeah, okay. So this is like, not like. Okay, so if we convert that now to a probability tree, we find 0.5, 0.5, and now these are conditional probabilities. So that's 40 over 50, so that's 0.8 and 0.2, and down here we have 0.4 and 0.6. So these are now conditional probabilities. And so if we want the joint probability, we can just multiply down. So this is, for example, now 0.8. This is just the probability of liking football given you're a woman. And this, for example, is the probability of not liking football given you're a man. So we've turned the frequency tree into conditional probability tree in that direction. Let's just check, shall we? Okay, let's ask the females in the audience, who likes football? 2. And the females in the audience who don't like football. You've got to be one or the other. 1, 2, 3, hands up, hands up, hands up. Great. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 or something like that. So in fact, in our real frequency table, we've got something like 2 and 13. Males, who likes football of males? Whoa! Lots. Who doesn't like football? Hey, yes, yeah, exactly. Great. 3 of us. Cool. Right, okay. 3 lots. This is precision math here. Okay, so these were not great probabilities. I wonder how I did my sampling. Now, okay, so they're not a should we say they're not a representative sample I had. Now the crucial thing is that that's just viewing the table in one direction. It's viewing as one structure. We picked the men, the gender, and then looked at whether they like football or not. But we can also do it the other way round. We could look at, first of all, see whether people like football or not. Now, it's quite an odd way to do the sampling, but we could do, 60-40, exactly, thank you. So we do 60-40, this is first of all asking for B, and then within that we can ask about what their gender is, so that's 40-20 and 10-30. So we go 40-20 and 10-30. And we end up, the point is that the joint probabilities end up to be exactly the same. But now what we've got is the conditional probability of being female given that you like football is 0.4. The conditional probability of being female given that you don't, no, this is the probability of being male given you do like football is 0.2. Have I got this right? It's so easy to get this wrong. Is this right? Yeah. And so the conditional probability of being female given you don't like football is 0.1. And the conditional probability of being male given you don't like probability is no, it's not 0.1. What am I talking about? I've got these wrong. It's 40 over 6, sorry. It's 40, that's 2/3. And this is 1/3. God, I knew I'd get this wrong. This is 10 over 40, which is 0.25. And 3 over 40 is 0.75. Is that all right? Have I got it right now? You've got to correct me. I will get things wrong. So we changed the conditioning around, changed the order. And that's known as Bayes' theorem or Bayesian analysis, where we reverse the order of the conditioning. We're told, in a way, something in a second, and then asked to infer what actually gave rise to that. And we get these problems, and we're going to have quite a lot of these problems coming up. There's a little one in the question sheet, but they will get more complicated. And as we'll see, we can turn this into a whole theory of statistical inference, ideas of induction there. Okay, so that's reversing the conditioning. And we'll be doing that more formally later. Okay, the other thing the other rule that we can get from these ideas is the idea of what's known as a decomposition result. What's the overall proportion liking football? Well, liking football is that and that. So the overall proportion, which is 60% like football, comprises 2 groups. There's the 50% of women, and of them, 80% of them like football. And then there's the 50% of men, and of them, 40% like football. And we end up with 60. So these probabilities down here, we can add up. 0.8, 0.1 is 0.4 there. Joint probability there, 0.5 and 0.2 there. And we get 0.6 as a joint probability. Now, as a probability rule, it's just doing that. And there's a lovely old phrase I was taught to describe this. It's been called extending the conversation. A really archaic old phrase, extending the conversation. And that's what I was taught for this. And we will be using that a lot when we get onto Bayesian statistical inference. Very strange. I don't know where it came from, extending the conversation. Bizarre. But it's just taking a probability for an event and decomposing it by conditioning on another event. And that can be incredibly useful to go either way, when we know these and we want to get that, and also when we know an overall probability and we want to deconstruct it. So we'll come on to that as well. Okay, so yes, just, I think this is almost come down. We've gone a lot faster than I thought we would. Okay, so the final thing I just want to mention is about what is probability? What does it actually mean? Now, mathematically, we learn probability as a set of axioms, and they produce rules, and we can use them. But we tend in maths not to be discussed very much. What does it actually mean? And I'm quite interested in that. I think it's quite important. So I just want to put up here 3 possible meanings for it. And I'll tell you which one I like, what I'm going to try to persuade you about. There's this one, which is the earliest one, which is just the fraction of events, as we'll deal with tomorrow, equally likely events. So you've got throwing dice or cards, when you can count the possible outcomes, when you can draw these trees easily just by counting the events. So in other words, you can just by reasoning, you can work out what the probabilities are. The trouble with that is that it needs some definition of equally likely. That is something that the coin is equally likely to come up heads or tails. And that's a big assumption. It may not be true. Which I'll show you tomorrow. Actually, I wonder if I got it here. No, sorry. Do that tomorrow. So that's an old definition, but I really don't like it at all because it's circular, because it needs to do the equally likely. There's this one. This is a classic definition, which is, if we carried on long enough, what the proportion would tend to. I know there's a long-term relative frequency, LTRF. But in general, we don't have an infinite time or an infinite number of replications. We're talking about unique events on the whole. What's the chance of somebody living a certain length of time? What's the chance of something happening tomorrow? We don't have all these infinite replications. And we're left with this one. This is the one I like, which is essentially we're talking about what are reasonable odds. It's a judgment about what do you think are the reasonable odds of something happening. And the easiest way to illustrate that is in this table. Let's say we believe this. We don't believe it, but what's the chance that the next man I meet likes football? Well, if we really believed this was representative, we might think, oh, that's about 40%, the chance of the next man. But he either does or he doesn't. His opinion isn't chosen by, it's not like flipping a coin. He either likes football or he doesn't. So in a way, there's no chance involved in it at all. It's just something I don't know whether he likes football or not. This is how I do this. Okay, let's do a little experiment on a coin. Okay, so so this is a fair coin. I do have a double-headed coin with me, but this is a real coin. What's the chance this will come up heads? Is there a head? There's no head. You haven't got a queen. Okay, I'll throw an English coin. Okay, what's a head? There's an animal on here. Okay, some animal or other. What's the chance it'll come up with the animal? Half, right. What's the probability this has come up with the animal upwards? What did you say? Well, you don't know. Do you? Do you think it has? Yeah, exactly. So some people are saying a half, other people are saying it's either 0 or 1. They're both, because it has or it hasn't, and there's no chance left in it at all. Is it got a probability? But you don't know. Okay, here, let's make it even nastier. What's your probability this has come up heads?
1.
Yours 1, somebody says. You may be wrong. Does anyone think it's a half still? Yeah? Yeah, it's a half still. It's not for me, it is for you. Well, actually it did come up heads, so you were right. But you might not have been. You went for one. I was a good gambler there. what we've done is actually do something very subtle, which is change it from before I throw the dice, it is chance. I mean, it's sort of, we can't know. We can't know what's happening, what's going to happen. Afterwards, after I've thrown, so beforehand, it's can't know. Afterwards, it's don't know. It's happened, it is either 0 or 1, but you don't know which it is. But I can look at it, so we've gone from can't know to don't know. And I can look at it, and then what you realise is that don't know, which is sort of ignorance, depends on who you are and what your knowledge is. So we've actually, what one says is that the first sort of uncertainty is chance, and the second sort of uncertainty is known as epistemic uncertainty, from the Greek meaning of knowledge. Epistemic uncertainty is when the uncertainty is about things that are true, but we just don't know what they are. They're not random future events, they're just things we don't know. Now, and what I'm saying is that this is actually the situation in many things. One of the things I hope we'll get onto is discussing about, as I said, I'm a medical statistician, so I deal in mortality rates and things. So one of the big questions is, what is, for example, the maternal mortality rate in certain countries? So how many women who die giving birth? It's a very controversial, important issue. Now, there's no chance there at all. It's just an unknown quantity. We don't know how many women. It's pure epistemic uncertainty. What is the actual mortality rate in a country? But we use the whole framework of statistical modelling with probability models for that. And if you look at many problems, you realise actually they're not to do with chance, they're to do with epistemic uncertainty. But we use probability models for them. They're things that actually have happened. We don't know what's happened. Sometimes, when we're really predicting the future, like weather or financial stuff, yeah, there's some real chance. But a lot of the time, it's to do with what we don't know. So what I would argue is that from a mathematical point of view, there's no difference between before I throw the coin and after I throw the coin. From a philosophical point of view, they're very different. But from a mathematical point of view, they're equally valid uses of probability. And we will actually be using it a lot for this rather than the before the coin. So it's a slightly philosophical issue, but it sort of shows that this subject is a lot broader than just coins and beans. It's to do with what we know and what we don't know. Okay. Is that... I'm going to stop. Are there any questions? I've just been going, rattling on at a great rate. And I'm afraid I haven't... you haven't been doing very much, but you're going to start. You're going to start doing stuff now. So the idea is that now there's a problem sheet that's... Let me just... Actually, I'll call it up. I'll call it up. Sorry, are there any questions before I'm racing on? I think I'm a bit nervous, so I'm going very fast. I'll just shut up for the moment. Yeah. Oh yeah, absolutely. This is a very important point. How did I do it? Well, I got it wrong at first. The crucial thing is that we got 50 who went down here, and then of those, 40 went down there and 10 went down there. So what we do, when we're turning this from a frequency tree into a probability tree, we take the 50 and look at what proportion went down there. So this is 40 as a proportion of 50. And the point 2 is 10 over 50. So this is 10 over 50, and this is 40 over 50. So it's the conditional, it's given you've got here, what's the probability of continuing? So it means that the overall proportion, so this is the probability of A, and this is the probability of B, and the overall proportion, which is the probability of B and A, is just the probability of A times the probability of B given A. And we end up with the joint probability, which is the number in that cell. So now it's a tricky point, especially when we start, and this is where I got it wrong, when we start doing the tree the other way and say, okay, first of all, we'll ask people whether they like football or not, and we get 60-40. Of those 60, 40 are women, 20 are men. Then when we want the probability of being a female given you like football, you have to divide that by that to get 2/3. So that's the trick, and is what we'll be doing mathematically a lot, but this is just how you structure it to see. And it's really, when I look at a cross table like that, am I looking at it this way or am I looking at it that way? Which way, which sort of projection I'm using for it. Oh yes, because these are the conditional probability, but each of those will sum to 1. Absolutely. If I do the joint, maybe I haven't written it out very well. If I do the joint probabilities, they'll sum to 1. But the conditional probabilities on here will sum to 1 just within a branch. So I probably haven't labelled that very well, because I really need another column here, which is the probabilities when I multiply down the whole tree, and then I get the joint probability of A and B, which is 2/3 times 0.6 times 6 out of 10, which is 12 out of 30, which is 4 out of 10.4. So you're exactly right. That is confusing how I've written it, because we just got to distinguish between the probability of the joint event and the conditional event. Yeah, okay. That should be, this is A, and this is A complement. So I've come up here, I've observed B, that they like football. This is the probability of being a male, so it's of those 60 went down there, 20 went down there, so it's 20 over 60, which is 1/3.
Is this B?
No, that's B, and that's A. So this is conditioning on B, what proportion went down A complement there. Is that okay? So it's a bit like, well, on this table you can think of it as if I just concentrate on B, what proportion are male? So it's looking at that as a proportion of all of that. It's doing the same thing. As opposed to when I built the tree, I did it this way to say of females, what proportion like football? So I looked at it as a proportion that way. So whenever you talk about, you have to be always very clear when you talk about, well, females liking football, what proportion of those females like a proportion of what? Proportion of the whole population, proportion of females, or a proportion of people who like football. It's not always clear at all. You need to be very explicit what you're conditioning on. Very good, very good. Well, the strict Bayesian point of view says that it's always a judgment. You construct the probabilities. So you use your available knowledge. So, for example, on the coin, I would say it's 50-50. However, I might know something different. Yeah, it's called a prior probability, in a sense. You have to use your background knowledge and information to make the probability. But if I keep on flipping it, so let's think it's a bias coin. And we're going to be doing this week. It's a nice example. Let's say I don't think it's fair at all, so I don't actually know what the probability is. Then I can start saying, well, I don't know, but I'll just keep on doing it and learn about what the underlying chance is. But I could start off with actually not being. In this situation, I'm saying I'm going to say it's definitely 0.5, 50-50. But I might not know it's 0.5. I might have some deeper uncertainty about it. So it's the whole idea of Bayesian statistics is that it's a subjective theory. It's based on our knowledge and understanding and our judgment, which sounds very normal. The maths is exactly the same, pretty well. Maths is the same. But it does have this extra sort of interpretation idea, which a lot of people have a lot of problems with, because they think that science is an objective, it's all to do with objectivity. Bayesian work is explicitly includes some element of subjectivity, a judgment coming into it, that you state beforehand. So it's controversial. Because it depends on the beholder, like this business. If you always think of that, it makes you realize that what our probabilities are depends on what we know. And two people might have very different probabilities because they know very different things. Now, I know it's really tricky. It's very tricky for people, if you've been brought up, which is most people are, that probabilities are states of the world, not just they're external things, then that's a really tricky idea. However, there is this alternative view that probabilities are not states of the world. There's the most famous textbook in this was Bruno de Finetti, which starts off, it's called Theory of Probability. It's that thick, and the first words are, probability does not exist. That's what he says. I've written a volume that thick, probability does not exist. We have invented it. So that's quite an extreme point of view. I personally believe that. Except maybe at a sort of subatomic level, then I think you could say that probabilities really exist at a sort of quantum level. They are determined, Stephen Hawking calls them determined probabilities. They really are, unless somebody finds there's some hidden states that of the universe that do actually generate these events deterministically, at a quantum level, people, I think, would accept that probability really does exist. There's nothing we can do about it. But at our personal level, our practical level, it's always a judgment. As I said, I got a two-headed coin. It's what you know is important. So we'll come on to this, and I hope to persuade you. There's some fairly simple questions with trees, because I think they are quite important to look at. Yeah, so I flip a coin, draw, the socks draw, the socks one. And then there's drawing socks out of drawers. To do the 2 dice 24 times, what's the chance of getting a double six? To do that mathematically, and then to write a program in SciPy. We're going to be doing, during the course, quite a lot of simulations, quite a lot in SciPy, to simulate throwing a dice 4 times and to repeat it. So instead of you having to keep on throwing the dice, to get the program to do it 1,000 times or 1,000,000 times, and to see what happens, to see what your number is. And so we have a go at that. Apparently, Emma says it can be done. There's what's the function? Random.randint. We'll draw a number at random between 1 and 6 with the right thing. So that should be okay. That's quite straightforward. This is a nice one. This is a beautiful problem, which is quite open-ended or quite tricky. So this is one for the people who've done it all before. You've got a drawer with white socks and black socks in it. And if I take 2 socks out at random, and the probability of getting 2 white socks is exactly 0.5. How many socks are in the drawer? So there's one to wrestle with. And I want 2 solutions. So that's quite tricky. So, okay, right, I'll stop. So what do we do now? Have a break and then go up to the practical room? The first few are on paper. I don't know if people would rather do them down here or go up to the room. Maybe even move up to the room. Is that all right? It's okay. Okay, and generally, I'm around. Please come and talk to me about any stuff that we do. Okay, cool. Thank you very much. Oh yeah, can I have my dice back?